Thank you very much. And so I just should warn before I start the talk, very unfortunately for someone giving a talk on a Saturday afternoon, I appear to be losing my voice. So apologies in advance if it's a little bit creaky or gravelly today. So yeah, thank you very much. The the title of my talk is It's Your Callable, Cool Parts of Python's Callable Interface. And like we just said, my name is Weldon, and I'm a cloud software engineer, and I'm based in central London, primarily. Now, this isn't my first time at Python Island, and every single time that I come to another country around Europe, but particularly on this island to speak, I always feel the need to instantly say sorry, mostly for the horrible Brexit mess. So this is me 3 years ago, and obviously what I couldn't have known back then in 2019 was just quite how bad things would get. They were bad then, they've gotten much worse now. So yes, it's been quite a 3 years, and I really want to say, particularly to the people of Ireland, thank you, so first off, for this whole Brexit debacle, I'm terribly sorry. But first off, also thank you for all of the brilliant memes that have been getting us through. These are followed closely, certainly by me and my family and friends in the UK. So thank you for the memes, guys. And sorry for the whole mess. I should say thank you also to Python Island. I can't imagine how much work has gone into organising a day like today. And a weekend conference like this. It has been such an ordeal to come through the last 3 years, and I'm really glad that we can all be here today. So thank you to the organising committee. Like I said, my name's Weldon. I'm a cloud software engineer. As I said, I'm based in central London, and I'm also an independent contractor. So I'm always interested in people who are doing cool things with technology who want to get in touch. I have worked for a long time as an associate with these people at Decision Lab, who are a mathematical modelling consultancy, and I have a gig at the moment as well for a financial services organisation where, if you believe Microsoft Teams, I am an expert software engineer, one that's just not been found out yet, but I'm not naming them here because I'm not here in any kind of official capacity. This is just a bit of fun of a Saturday afternoon. So, onto the talk, callables, or cool parts of the callable interface in Python. First off, why have I chosen this topic? Well, we say often that functions are first-class objects in Python. They're really fundamental to how the language works. And there are also quite a lot of tools that exist to introspect the callables that exist in the language and functions. And these are really kind of quite essential to how frameworks operate, and building and maintaining frameworks and interacting with them as well. So we'll cover that. To start off with, we'll do a very quick tour of callables. Then we'll look at how we can inspect callables and the metadata that exists on them. Then we'll look at how we can modify this metadata, and then we'll have a look at a couple of reviews and caveats if there's time at the end. So, on to a quick tour of callables. So, reasonable question, what do I mean by a callable? So, quite simply, a callable is something that we can call, and something with 0 or more positional and or keyword arguments, and it's something that returns a value for us. There are really 3 common ways of creating a callable in Python. I'm sure we'll be familiar with pretty much most of them, possibly not the one at the end if that's not something you've come across yet. We've got the standard def statement. There's the anonymous function that we can create with lambdas. There's also the call method that exists on classes and objects that you can add there. In this talk, we're covering pretty much the part of the function there that's highlighted in red. There is also this thing down at the bottom, that self argument that exists on classes and objects. We're not going to cover that today. That's something called the descriptor pattern, but it's well worth checking out if you're curious. So this def line that we've looked at here is different from other lines in a function in that it's executed at import time. Now, that's really important because when you import a module in Python, all of your def lines are executed, but obviously the code inside of your functions isn't executed until you actually call your function. And that's significant for a reason that we'll look at in a little minute. If we look at what actually happens when we call that def, when we execute that def line using a tool like dis, you can see that there's a few things going on here. The first is that we're creating a code object, and we're creating a name, which in this case is f, and then we're assigning that code object to the name f. So you can actually, in that store fast procedure at the bottom down there. Now that doesn't, you don't need to know too much about the fundamentals of how that works, but you can inspect some of these attributes that get created on the object that we've made here, this f. We've got that code object that we can look at, and we'll look at that in a bit more detail in a second. And we can also find out the name of our function here, because it's not an anonymous function, it has a name. So callable, I should say as well, callables can be created in other languages. You can use C if you're feeling brave, Rust if you're sensible, Java if you're antiquated, and Go if you're just feeling a bit wacky maybe. But we won't cover that in this talk here, but safe to say that most of the metadata that exists on these types of callables is also accessible in the same way that we'll cover here. Now, some of the more awake in the audience might be asking, hey, what about all this async stuff? A lot of functions these days, pretty much most functions you'll write are async. And the short answer to that is that we're talking about callables here. We're not talking about awaitables. So here we're talking about everything that happens up until the point where you call your coroutine function to create a coroutine or a future, but we're not talking about actually awaiting that future or that coroutine. That's something for a whole other talk if you wanted to do that. And there are functions that you can use in the standard library, in particular the inspect module where you've got is coroutine function, is awaitable, that kind of thing. And you've also got the built-in method callable, which tells you whether or not you can call something quite simply. Now, here we're going to look at the difference between creating a callable and using a callable very briefly. Now, there is quite a significant difference here. When we create a callable in Python or a function, that's a statement. We're not actually returning a value there. We're literally just executing a bit of code to build something up inside of the language. And the relevant syntax of that is defined in section 8 of the Python docs, which is language fundamentals, I think. And you can find that in a bit more detail there. And we'll actually look at that in a moment as well. But when we define a function, we say that it has 0 or more parameters. Now, when we call a function, though, that's actually an expression. We're mixing together the function and any arguments that we're passing to it to create a new value, i.e. the value that's returned, even if that value is none. And rather than passing parameters to a call, we pass arguments to the call. And these arguments, and this is all detailed in a different section of the Python docs here, but these arguments are then matched to the parameters that exist inside of your function. And there's a slightly convoluted explanation of how that works inside the documentation. And there's an algorithm to sort of deal with potential confusion that can happen there. If that fails, and we can't match the arguments that we provide to a function's parameters, we raise a type error, or Python raises a type error for us. So you can see as well, if we look at this example function, there's actually quite a lot of other bits of metadata and things that we can do. You've probably seen functions like this where you've got variable numbers of arguments, or positional arguments and keyword arguments. We've also here got a docstring that you can look at as well. So this is really kind of the fundamental stuff. We've also got the keyword-only arguments that can be specified. I think they've existed in Python for a while now, and as of Python 3.8 a few years ago, you can also specify a positional-only argument. So the arguments at the top there, C and D, they can't be passed as positional arguments, whereas A and B here, as of Python 3.8, they can't be passed as keyword arguments. So you can tighten up your interfaces using that feature there. And likewise, if you try and call a function incorrectly here, you'll get a type error because you can't, for example, pass a positional-only argument as keyword. As of Python 3.6 as well, we introduced, the language introduced type annotations, which you can see up here. So these are not enforced at runtime unless you're using particular specialist languages and frameworks. But these annotations do provide, I think, a lot of metadata about what that function's meant to be doing here. So even just looking at that function signature, you have a rough idea of maybe what is happening. You're going to say hello of that string a certain number of times according to that integer, and you're going to get a string back as a result. Now, we can provide a lot of really detailed metadata or information about what a function does inside of that metadata, inside of that callable's signature and interface there. Frameworks, so think of things like Fast API, Pydantic, PyTest, lots of the big libraries, Django, Flask, that kind of thing. They use this metadata to implement the features that exist inside of the framework. You can also alter that metadata in order to enforce or in order to interface with some of these existing frameworks if you want to change how that works. And we'll look at that in a moment or two. So let's just first off look at how we might start inspecting some of the metadata that exists on a callable that we're looking at. Some of these you'll probably be familiar with, so let's look at what metadata exists. I'm going to use this example callable here where we've got, we're just multiplying 3 numbers together, but we've got 3 arguments of different types. There's a positional only argument there, positional or keyword, and keyword only argument, and it's all annotated with a doc string. You can access all of this, this data. You've got your simple name dunder, doc dunder, dunder qual name or qualified name. So if this function was inside of a module, you can get the full address of that function using that. You've also got the default arguments that exist there, and the keyword default arguments that exist. And these are actually used, in particular if you've ever used the dependency injection framework inside of Fast API, that hacks this particular interface to make more declarative code that you can use. So that actually uses these defaults as a way of passing arguments to your framework. And you've also got the full annotations that exist there. So broadly speaking, you can look at how those different dunder properties, the kind of fundamentals, map to different parts of the function definition or the function signature here. And these are some, but not all, of the metadata that exists about potential different types of functions inside of Python. So, now we've said before that callables are first-class objects inside of Python, but I mean, if you're on a train, you have a rough idea of what a first-class carriage is. It's the expensive one with no one in it. But if you've got a first-class object in Python, we need to think, what is that? And so there is a definition, and it's simply an object that can be constructed at runtime, passed as a parameter, returned from a function, or assigned into a variable. Now, that has consequences for how functions operate and the metadata that we can get out of functions as a consequence. Crucially, it's because functions can also be nested inside of other functions. So this is actually quite a common pattern inside of Python. It's a little bit more common if you're familiar with JavaScript and things like arrow functions or closures as well in Rust. Or, ooh, got a bit of a disco going on. There we go. So let's have a look at this function here. We've got the enclosed function, which is a child of the enclosing function there. And so we can see that we've defined a function inside of another function. So that def line is actually, the second def line here is run when the enclosing function is executed, or is called. And here we can see that we're returning the first function as the return value of that enclosing function, and then when we call that value that we've gotten back, we get that value 1 there. Now that's all very well and good, but it can get a little bit more complicated. So functions, or child functions, have access to their parent's scope. So here we're defining a variable x in the scope of the parent, and we're using that value, or that variable x, inside the child as well. All well and good. X is defined in the parent scope. Boom, we've got our 1. Now let's have a look at this. Who thinks, what do we think about this code? Let's take a quick show of hands. Who thinks this code's going to run handy-dandy, no problem? Or is everyone being very brave? Or no? Okay, does anyone know what kind of error this is going to throw? A variable error of some kind? Yeah. Ooh. Bang on. Yes. yeah. So, yes, this is. Oh, he says spilling his water slightly. Yes. So the problem we've got here is that we're defining x inside of our parent scope, and inside, but we're also creating an assignment inside of the child scope as well, which is also x. So when we come along to the first line here, Python's going to try and evaluate the right-hand side of this this assignment first, and it's going to say, hey, I'm trying to use this value x. I'm trying to find this this variable x. It's in the parent scope, but I'm also assigning it here, and I haven't used it yet. So it creates this special unbound local error. And the way that we can fix an unbound local error is with the non-local keyword, exactly. And so here we can make this function work, for example, using non-local. However, when we have these enclosed functions in Python, non-local tells the Python to look in the higher scope. So Python calls these enclosed functions closures. And we can actually also get metadata about these closures and the nested functions that exist on dunder methods inside of Python as well. And so if you've ever used a Python debugger, quite a lot of the kind of debug machinery and instrumentation uses this sort of setup to be able to analyze what's going on at particular points inside the stack. So here we can see inside of this closure dunder property here, we've got a cell, which is a kind of a code block inside Python. It's an object, and we can look at the contents in there, and we can see how the variables change as we iterate through, for example, inside of a loop or something similar there. Now, this information all broadly relates to a callable signature. And Python, as well as the dunder properties, we've got a very nice little interface into a Python a function signature using this function inside of the inspect module, which is inspect.signature. And that will return a signature object with a capital S this time for a given callable. And that provides all of the kind of information that we've seen inside of those dunder properties, but this time as a handy object that we can analyze and sort of interrogate using Python. Each of the parameters as well, I should say, that we create as a result of that, you can see inside that dictionary there, they're also individual objects that we can look and play with and create and edit to our heart's content. So, which is, you can see here, it's the inspect.parameter that can be used. And we'll leverage that in a moment to do something fun. So we've covered signatures, broadly speaking, inside of functions, but there is something missing from the function definition that I've not covered. And if we have a little closer look at the documentation, we can see here, right at the top, decorators. Now, decorators are important inside of Python because you can see the exact syntax of this specification here isn't really important. But the crucial thing about decorators is that we can use them to wrap a callable. And like that def line that exists inside of, that we talked about earlier when we're creating a function that's run at import time, decorators are also run at import time, and that means that we can use logic on our decorators, or inside of our decorators, in order to do all sorts of weird and wonderful things. So the decorator is called when the def statement is executed, like I said, and they allow lots of frameworks to, for example, register code on a bigger global object. So if you've ever used a framework like FastAPI, I'm sorry, I work with FastAPI a lot, so it's always my go-to. But if you've ever used, for example, that root decorator, that's exactly what's going on here. So let's have a look at how decorators work. You've got the standard at syntax there. It's a little bit of what we used to call syntactic sugar. And broadly speaking, a decorator is really just a function that returns another function that can get called. But just before we look at that in a little bit more detail, there is something new, and this is one of my newest favorite Python facts as of, I think it was Python 3.9. So if you have a look, this is the definition of a function, or the syntax for declaring a function in Python 3.8. And you can see here that a decorator is specified as a dotted name, so that's a kind of address to a callable that exists. If we fast forward to Python 3, it says 3.9, yes, there was a PEP that got approved, PEP 614, and that decorator is actually changed from a dotted name to an assignment expression. So you can actually write some you can use assignment expressions inside of decorators, and as a result you can write some really wonderful, weird and wacky Python, which is valid. So, for example, if you really, really dislike your colleagues, you can start writing code like this, and it's a great way to get sacked. But that's not as hard as it was these days, is it? So, yeah, please only do this if you really, really dislike one of your colleagues, or all of them. But still, so. Moving on, let's look at some of the decorator or some of the metadata there that exists on our callables and how we can use these inside of decorators. So I'm going to create a decorator function here. It's called announce call, and literally all it's going to do is say, hey, I'm about to call this particular function. So we take the function at the top as an argument to our decorator. We return this wrapper function, and we just say I'm calling this func.name using that f string there. Nice and simple, and you can see the result works. We say we're calling this function. You can write functions like this to do, time how long something's going to take, or sort of, put emojis in your terminal or something like that. It's a useful little pattern. But how does, you can see here inside of our decorator, we're actually defining a new function. We've got a whole new def statement there. And so I'm wondering, how does that affect the metadata that we want to get from our new function that we're returning? And if you have a look here, we can see that this signature, when we call that signature method, we've got no useful metadata there anymore, because we've got basically, we're just saying this function is going to take some arguments, and all of that metadata that we had previously is lost. Now, almost every good tutorial that you'll ever read about decorators in Python will tell you, oh, it's cool, just use this thing called functools.wraps, and that'll sort it for you. But I kind of think that's a little bit lacking, really. It's quite important to know exactly what happens when you use that method, or that functools.wraps. And so we can see here, obviously, we can fix the problem with our metadata there using our functools.wraps. But how does it work? And so, quite simply, like everything in Python, it comes down to dunder properties. And in this case, the dunder property that we're looking at is wrapped. So functools.wraps will create an attribute on your returned function called, quite simply, wrapped, and that is a pointer to the original function. And so if we then use tools like inspect.signature, or crucially inspect.unwrap, we can always find our original function. And so that means that functions can be really deeply nested, like this one here. We've got 4 layers of decorators. But if we're using a tool like inspect.unwrap to try and find our original function, it's quite straightforward, because inspect.unwrap will just look down this big long sequence of wrapped until it finds the original function. And so this is related to the decorator pattern. You might think, oh, all of this metadata is a little bit abstruse. But there are lots of libraries that really, this is the kind of the bread and butter of how they work. So this is just an example from Fast API here, where we're using that depends in the Fast API dependency injection framework. And you can see here that there's lots of code that's taking the parameters and sort of looking for default arguments and inspecting all of those signatures as a part of how the fundamentals of how it works. So we've got a lot of metadata about callables for us to read. But what about if we wanted to change some of that metadata that exists on these individual callables? So I'm going to set a quick challenge. We're going to create a decorator which actually adds a new keyword-only argument to an existing function, making it appear inside the function signature. So let's start off by looking at what the decorator is actually going to do. So the example here that I'm using is add a shout option. So all this function is going to do is add a new keyword argument to the existing function that we're wrapping, and that keyword argument is going to be called shout. It's a Boolean, and if it's true, this function will look for a keyword argument called name, and if it finds it, it'll create it'll turn that into an uppercase string. Now, if you're actually using this in any kind of real-world scenario, there's lots of other logic and testing that you'd have to do here, but this is just a down and dirty example. So, and you can see here we're adding a new keyword, doing some logic, and then we're passing the original argument back. So we can see the example on a function that will be eventually used here. So we've got creating a greeting and creating a farewell greeting. I am cheating here. I'm only using a keyword. I'm using a keyword-only argument here for a reason. If you want to do it with positional arguments, there's a little bit of logic involved, but it's easy enough to do. So how do we add this extra parameter to our function? So we've got the original code that I've made a little bit smaller there, so that's just the same code that was up before. But now we're going to add some special code here. So the first thing what we need to do is get the original signature object. So this is the signature of the original function represented as an object in Python. We're now going to create from the actual constructor of that class just an extra parameter. In this case, it's going to be shout is the name of the parameter. It's going to be keyword only. and the name of that parameter there is kind, because I think that there are just too many different uses of the word type in programming, so someone decided to use kind there. We've got a default value for it, which is going to be false, and we're annotating it with a Boolean. Now, the next thing we do is we use this replace method to create a new signature object, replacing the original parameters with a new list of parameters that I've created at the top there. Now, there is a caveat here, and it's a bit of a boring one, but the value of that sig.parameters is actually a mapping proxy, so you need to convert it into a list to be able to create a new one, but that's just a bit of a quirk of that inspect library and how it works. But so what we're doing here, so we've created a new signature. So just to recap what we've done in this code, so we've created our decorator. We've used the inspect.signature method to create a new, to get the original signature. We've changed that a bit by adding a new parameter, and we've created a new signature that we want to apply to our resulting function. So how do we tell Python, is the next question, that this wrapped function now has this new signature, even though it might be a little bit of a different one? And again, unfortunately, the answer is quite simple in Python. It's a dunder method, or a dunder attribute, simply called signature. So this signature property will alter the behavior of the inspect.signature method that we mentioned before. And will basically say that if you're looking to find out what the signature of this function is, don't look any further. I'm telling you what it is on this method, on this attribute here now. And we've obviously also put the wrapped attribute in there just to make sure that we can still follow things with inspect.unwrap. And so methods like inspect.signature, at each step they'll check to see if there is that special signature attribute. If there is, that value of signature is returned, and it stops looking further down the stack, like we say. So this is our function as we've created it, or our decorator as we've created it. And we can see now that if we call the inspect.signature on the newly returned function, we get the signature that we want with the extra keyword argument. But if we go down the whole way in the stack and look in that kind of the final unwrapped function, that argument disappears, and the signature is the same as the original function. And crucially, if we actually call the function, so I've got this create greeting function here, I'm not shouting, but if I do want to turn the shout option on, I can. And so the logic there has sort of worked, and we've been able to inject a keyword argument into an existing function. So you can alter a callable's apparent function signature using this combination of signature and the dunder property that exists there. Now, I suppose the obvious question is, why on earth would you want to do this? So, well, as a bit of context, the way that I stumbled across this was actually writing an integration between Pydantic and SQL Alchemy, and then obviously Sebastian Hamburger's library SQL model came along and scooped the project I was doing, which was obviously very frustrating. But there are lots of examples of when these sorts of sometimes a little bit hacky, but other times actually really quite useful ways of injecting and altering a callable's signature can allow you to work with existing frameworks and interface between them. So the conversion of dynamic objects between frameworks like Pydantic, SQL Alchemy, Fast API, like I mentioned. I also find that this is quite useful often inside of lambda functions to make them more declarative. So, for example, if you are writing a lambda function to consume a DynamoDB stream or something like that, and you want to add in your dependency injections, this is the way to go. Likewise, if you're writing a dependency injection framework, for all the fun that's involved in that, this is your friend. And yeah, indicating that you want to use, for example, a dependency inside of one of your decorators is often important here as well. There is a final caveat about all of the metadata that I've mentioned. There was a hoo-ha prior to 3.10. Back in mid-2021, I think it was, in something called PEP 563 that was going to basically convert all type annotations into strings and just completely forget about them as far as the runtime Python was concerned. That was resolved, and essentially the Python steering group now, or the Python steering group, have said that actually it's a perfectly valid use case to use type annotations inside of your runtime code, like Pydantic does, like Fast API does, and so you can use that kind of code safely. So just as a recap, there are lots of rich metadata that exists on callables. It's possible to modify this data at runtime to adjust the behavior of other functions. These are really essential, these bits of metadata, if you're writing frameworks or you're trying to integrate with them at a particularly difficult or advanced level sometimes. And despite some of the recent uncertainty with type annotations generally, it's perfectly legit to use type annotations inside of your code, like a lot of the Python code base does these days. So, thank you very much, and yeah, please do say hello. Cool.
We have some time for questions.
Why we need this? So what you have just presented, the ability to, for example, decorate in that way, the functions, and so on.
So just an example of why to...
Well, you say in Lambda is used, in other places is used in the frameworks during the conversions. But could you give us a simple example when you encounter this in your daily life, and how do you convince your colleagues that it was good to do that?
Sure. So I often tend to work in slightly constrained environments with unregulated environments as well, where we necessarily have to use particular versions of software or libraries that are approved in certain ways. And so sometimes using these are a slight workaround to be able to, for example, if you're working with a dependency injection framework, let's say, that requires you to specify, for example, what dependencies you want using the signatures of the object of the callables that you're passing to them, to be able to use, say, a connection to an outside DB or a connection to like a lock in some way inside of a decorator. For example, if you're needing to pull data or alter data to get a lock and then put it back, if you're making a transaction or something, that a lot of the time there you will have to basically just hack around a little bit and say, I'm going to add an argument to this function now. But in terms of using reading the metadata that you might want to use, I actually use that all the time. So inspecting what's on a callable there, absolutely essential. So I write a lot of, in my kind of day jobs, I write a lot of code which is used by quantitative developers to work in, sort of data science or analysis fields, and being able to say, oh, wrap your function with this particular decorator, and I'll just pull out everything else that you need, connect to all the databases, and fix it. That is really essential and cool. So, yeah.
Could you use also the cherry bullet runtime?
In order to, sorry? Yes, interrogate what's going on in code and perform security checks and that kind of thing as well. You absolutely can do that using, not just using the inspect library, but using other parts of the code too. But the gateway into that is definitely inspect. So, cool. Thank you.
Yeah, quick question. I'm using a framework called Modal, and I don't know if you're familiar with it. It's like AWS Lambdas, but you annotate to say, okay, give me this image, Ubuntu, pip install these libraries. But I want to run it local. I've been trying to run it local. So I want an option to run local or to run remote. And what I end up doing is hacking out, having a global variable, local or remote, and then putting modal inside a function and the annotation inside the function, because if it imports the annotation, it imports the runtime, which runs it in the cloud. And I want to run it locally. So my question is, how do you do conditionals in annotations? I'd like to have an annotation which conditionally runs this other annotation, and if that makes any sense. So it's wrapping an annotation inside an annotation at some level. Yeah,
I think so. Do you want the, oh God, the word's just gone out of my head. What's the, it's not a generic, the one that's along a generic, it's not prescription or something. Yes, there is absolutely, so you can do with that. And I've bloody used them in the past, but it's just completely gone out of my head. It begins with a P, the protocol. Sorry. If you tried using typing protocols, and that would be the direction I would go down, because you can then include some like quasi sort of logic inside of them. But yeah, happy to have a chat and stuff. Cool.
Thank you so much.
Thanks so much.
Yeah,